How are you guys doing? Everybody get out there. Yeah, you're doing good? All right, that's more like it. Y'all get out and vote today, I hope? Or got it planned at least? No? Really? You guys, you voted early. All right, me too. Me too. Yeah, well, do it. At least I know it sort of feels like the year without an election, but those local issues matter. You can actually, if you study those little pamphlets, you can make a difference around here at least. All right, I won't belabor that point. You guys know how the show works. I want to hear from you about last week. We were talking about magnets. What did we do before magnets? Somebody remind me. Oh, yes, the heretical science of the expanding Earth. That's always a good time. You guys have time to process either one of these ideas, and yeah, let's talk about it. Yes, you're ready to go. Remind me your name again. Sorry. That's right, Macy. I should learn these things. Sorry.
The idea of like, yeah, they did together pretty well, but with the expansion, but they put together a lot better. So I thought that was really good.
It's pretty uncanny. It's weird. Yes, Orlando.
Or explanation of how the magnets work.
Yeah,
It's really interesting.
interesting.
But
All right, I want to go through it one more time just to make sure it's sunk because we didn't get to talk about it with respect to the Earth itself, and so I want to make sure. Um, Other thoughts? Anybody? Well, yeah.
Trying to remember the discussion we were having on, like, we were talking about how the old atmosphere, they were saying, well, it's supposed to be thicker, so, what we were debating, I'm just trying to remember it at all. All I remember is like, what I wrote down here is Don Petit saying that we have a thicker atmosphere density to make big things fly.
You guys know Don Petit? Have you seen him before? No. All right. He's one of those astronauts who like shot him out on NBC and stuff up on the. He's the oldest astronaut to ever go to space, and he's from Oregon, so he shows up in the news and stuff a lot. So Don's thing was how the hell do these winged dinosaur things fly? And the only thing that him and his advisor at University of Oregon could come up with was that the atmosphere was 3 times thicker during the time of the dinosaurs. Uh, the alternative, the argument from the mainstream is that they didn't fly. And then the question becomes, why the heck they got wings? They don't fly. And they couldn't even really glide either, is the other argument, right? So we have things like those flying squirrels, which are awesome, by the way, but they glide quite well. They jump off trees and cliffs and stuff like that, I think. I don't know. We don't have any around here. But I had a friend who had one in his apartment. It was kind of amazing. They couldn't do that either. So their only explanation was that. And then, of course, this opens this whole can of worms of like, oh my God, if the Earth was actually had a 3x thicker atmosphere. Now remember, it would still feel the same. You would be able to breathe it the same. In all honesty, like you don't notice you're under a tremendous amount of pressure from the atmosphere right now. Why don't you notice? Anybody?
Well, we were like born that way.
Yeah.
Just live that way.
Yeah, exactly. So the simple physical answer is that every part of your body is already pressurized. Internally, it's pressurized. Externally, it's pressurized, and there's a nice balance there. But if you were to take yourself and put you in a vacuum, right, outside of the atmosphere, your body would explode, basically. Of course, it would freeze too. It would be a real mess. You've probably seen this in every sci-fi movie ever, but it's not good to depressurize a human really fast, right? And you see this actually, well, you might not want to see this, but if you look at sometimes they'll drag these, they'll catch these deep sea fish in these nets sometimes, and they'll bring them up to the surface. Like sometimes rockfish live like, I don't know, 1,000 feet below the surface, and they'll bring them up to the surface and they'll pop. It's really gross. Yeah. Blobfish? I don't know what blobfish is.
You don't know what that is?
Oh, I don't know what blobfish is. Oh, oh, come on. All right, we gotta look this up. Blobfish? All right, but you're saying they look like a puffer fish type thing. No. No? I mean, this is a pretty crazy look. This thing. It's either ugly or adorable, depending on how you cut it, I guess.
Well, that we make one of them.
So they're deep sea fish. Okay.
But that's not true.
I think they're kind of cute. I could see it. Look at that face. I mean, the point is that you could actually, as long as you evolved in an atmosphere that was really thick, it wouldn't be a big deal to you. It would make gravity feel a lot less to you, though, because you'd, of course, displace a different volume of it, and you would have more of that buoyant effect, sort of like when you're swimming on the ocean. So that would be really quite interesting. And so I guess the fascinating piece of this is that when Carey was fighting Wegener for the theory of how the continents moved into their present locations, right? Because like everybody agreed that they must have moved, right? There's all these overlapping fossil seams, overlapping mountains we talked about. Everybody agreed that they used to be somewhere else. And when they were debating about it, they didn't have a mechanism for what in the world would cause the Earth to expand. And so what's really interesting about work from guys like Don Petit is that if the atmosphere was 3 times thicker only 65 million years ago, could it have been 10 times thicker, I don't know, 100 million years ago? Could it have been 1,000 times thicker billions of years ago? Right? And if it was, then you might have a situation where the Earth would actually be compressed by all that additional gravitational tension, essentially. But it'd have to be really, really big. We're talking like the size of like a small, like a Neptune-like planet, essentially. But you guys are starting to pick it up. There's this really interesting metamorphic idea that's creeping into the edges of planetary science, and I think that it's going to be. I think it's very promising. You know, no, like all these things are theoretical, right? The question, and oftentimes the different stories do line up with the evidence. The question is which one makes the most sense to you at the end of the day, and then of course once a particular theory makes the most sense to the most scientists, then it becomes kind of the mainstream talking point. It'll end up in the textbooks and all of that. So it's an interesting idea. I don't know if it's true or not. But like I said, those convection belt things for the continental drift have failed to prove out. And so it's not clear that there's a mechanism for the continental drift thing either, I guess is where I'm at with it. Kind of interesting. Thoughts, concerns? That's probably yeah. That theory, at least, is one of the more out there ones you'll hear on this class, but might be something to it. Thoughts? Guys are sad today. Is it the election? What's going on? God. Come on. We'll be all right, people. Either, whatever happens, there's another election in 4 years. So, if your particular choice doesn't work out, you'll have another chance. Okay. Good grief. All right, I got to call on some people's names because I want to get through this other round here. Let's see, Sophia, are you here? Nope. Shay, I saw you here. You talked already though, but give me another thought.
Like magnets.
Yeah, sure. Give me a thought about magnets.
They confuse me.
Yeah.
And I don't get how, so the Earth has a magnetic field, and they say that's because there's a big iron ball in the inside. But why doesn't Mars have one? How did Mars lose its magnetic field?
All right, so we'll talk about the planetary magnetic systems here. That's the first thing I want to deal with. I got a couple of slides because we didn't make it that far. And to answer your question, Mars is a little bit easier to explain because it seems to be quite a bit different than Earth in that it doesn't have active faults and active volcanoes and stuff like that. Venus is a little bit weirder because everybody seems to suspect there's a lot of volcanism and a lot of tectonic business on Venus. And so the mechanism that we're going to talk about is essentially that you set up that solenoid system by all of this swirling this swirling charged material, right? You have all this fluid metallic stuff swirling around, which is essentially, to dumb it down, it's essentially lava-like stuff, right? So if there's a bunch of that on Venus, Venus has the same density approximately as Earth. why doesn't Venus have a magnetic field? That's really, really weird. Mars is like I said, it looks, you know, on its face, it looks a lot older. Of course, the story is that all the planets are formed at the same time, but it looks like it's been inactive a lot longer, at least on its face. And another way of putting that would just be that something changed a much longer time ago than it did with Venus. But yeah, it's very, very, very interesting. And so part of this system has to do with the core too. We're going to talk about that. Yes.
Magnetic system, like if their core is made up of something else, like maybe it's not visible to us, but some other element is acting like a magnet to that element.
Could be. Yeah, so we didn't really get to talk about it last time, but iron. So the cores are thought to be iron. Our core is certainly thought to be iron. The cool thing about iron, and nickel does this too to some extent, is that if you stick it, so that little electromagnet I made for you guys, I showed you a little electromagnet system that when you charge it, it repels against the magnet, spins. This is how we generate power for the most part. The thing about that, the only reason it works is because as soon as there's no current flowing through those wires, there's no magnet. So there's only a magnet present for that instant where the wires are connected and it's charging those coils and then it kicks off the magnet. Then there's no magnet in the solenoid while it's spinning. And then it touches the contacts on the shaft and a new magnet appears which repels it against the static magnets. So that only works because the magnet disappears as soon as the current's gone. What iron does is if you stick it in the middle of a solenoid, it has this strange ability. It has an almost jello-like property with magnetism that it will be trained by the magnetic field that surrounds it. And it'll stay. It'll essentially amplify that magnetic field, but it'll also stabilize it. So if you turn off the current, a fair amount of that magnetism will still remain. Right? Because you guys have probably like magnetized paper clips or something accidentally before just for fun, right? So you can magnetize iron, nickel, you can magnetize certain metals and they will stay ingrained. They'll be like trained to act like this magnet system, the electromagnetic system that was passed in their vicinity, right? You can do it with another permanent magnet too. So what's really interesting about the iron core is not that it is the source of the magnetism necessarily, but that it stabilizes it, which is quite interesting because look, the sun has a really powerful magnetic field, but it's really unstable. It's bistable. It flips every 10 years or so. Makes a full reversal, I think, every 20 years. So that would be, I don't know if it would be problematic on Earth, but it would certainly be a very different situation. It's unclear how much of our infrastructure really depends on that magnetic field being the way it is, but certainly animals use it to navigate. And it's nice that it's stable too, because when the magnetic field disappears, even on the sun, when the magnetic field inverts and changes north to south, there's a brief moment where it passes through like a really low minimum. So there's basically no magnetic field. Now that happens on Earth, but it doesn't happen, almost every million years-ish or so, 700,000 years, something like that. So we have a really stable situation because of this iron core. That's the thought anyways. So again, it gets really problematic because Venus seems to have an iron core too, from what we can tell. Of course, a lot of these estimates come from density-based stuff, right? You're really just trying to reconstruct the planet based on how massive it is and what you think it's made out of, which is tricky. So, yeah. Well, let's unpack that more in a second. Any other thoughts?
Might be getting into this, but I think you're talking about it. So if the iron or nickel that's in the core only stabilizes the magnetic field, is it some kind of rotation in the core that is the actual cause?
Exactly. Yeah, it's thought to be the outer core actually. So there's an electrified, let's say a charged system outside of the solid core. So we think there's actually two pieces to it. And that, again, comes down to a lot of those seismic studies and so forth. And also trying to just come up with a mechanism that could generate this incredible magnetic field that we have. Yeah, we'll go through that. We'll go through that. Make sure you understand that. Any final thoughts on basics of magnetism? I'm gonna go. You know what? Let's just do it. Let's just make sure that everybody understands what we talked about. Okay, before I do that though, I wanted to bring up one really interesting thing. So a lot of this, as you guys can tell, is coming down to looking at data and then fitting patterns to it. And then the final step is, of course, trying to connect what the pattern is to what it means. What are the actual natural actors doing? What are the atoms doing, right? And this is the part that we don't often hear about in your chemistry or physics classes. And that's why I was trying really hard to put a physical model on this magnetism thing, at least so you can visualize it and understand what the atoms might be doing. I had a friend the other day who was trying to ask ChatGPT about the difference between math and science. And I thought what it gave back was really interesting. I wanted to share it with you guys. Chat wrote, mathematics focuses on internal consistency within a logical system. It's about developing frameworks and structures that hold together based on agreed upon definitions and axioms. In this sense, math explores what we can believe within its rules, ensuring that each result follows logically from the initial premises. Science, by contrast, aims to uncover truths about the external world. It's not only about consistency within theories, but about testing these theories against reality to see if they correspond accurately to observed phenomena. Therefore, mathematics gives us an internally coherent system, while science checks whether these systems align with the evidence and the nature of reality. I thought that was a really interesting delineation between those two. The one piece that's missing, though, of course, is yes, you can look at a theory, right? You can look at continental drift and you can look at expansion and tectonics, and you can see whether they're internally consistent, and you can see what sorts of pressures would be necessary to accomplish them and so forth. But at the end of the day, you still have to pick your favorite, because there's oftentimes two different theories that make sense for things, and that's really uncomfortable. But the reality of the fact is that in science, there's a huge interpretive step, and that's really, really tricky, but it's also really, really interesting too. Any thoughts on math versus science? Yeah. I like to say math is quantitative logic. It's kind of like a language built entirely out of quantitative adverbs. So yeah, you have to use your brain on top of math, unfortunately, even if you're the best mathematician in the world. And a huge crisis in physics that we're going to be facing down next semester is, well, it's really the fact that the mathematicians kind of took over the asylum in some sense. And mathematics itself isn't necessarily pegged to anything in physical reality. Yeah.
Then much more intellectual. So I was going to say.
Oh, I'm sorry.
Try to think science and the natural world into the barrier mathematics and try to make everything like line up as if it was on a grid. And then get frustrated with that.
Gets even worse next semester because people actually take those grids, and you can do incredible acrobatics with mathematics. You can make an infinite dimension parameter space and start twisting it around. You can do all sorts, especially because so few people can follow. I mean, how many people in here can do calculus really well, first of all? Yeah. How about differential equations? Like second order differential equation. Okay. All right. One person, and like you get into, multiple order differential equations and tensor math. There's like a handful of people who can follow these arguments. And so those arguments tend to get siloed away in these dusty, offices where really only a few people can evaluate them. And they can depart really fast from physical reality because of that, because most of the people who are studying physical reality are not mathematicians. And so it's very, very difficult to keep, especially when you handed over the keys of the castle to those people, it's very difficult to keep things real, so to speak. And so we have to watch out for that. And it doesn't seem to be a high priority. It's like, I talked about this last time, just going back to review magnets. I was talking to you guys about the surface of the atom, right? The electron with, its distance where you find the electron with respect to the nucleus. And it's like, almost all chemistry books will just draw like a nice orbital shell on an atom. But they're completely neglecting this tail of the distribution, right? And like, as far as I can tell, that tail of the distribution explains almost everything that's weird and magical and spooky about the atomic world. It really implies that the atoms are quite delocalized and they're actually in contact with their neighbors at the very least. And so we don't need some sort of weird ether thing that's separate from the atoms. We just need a better conception physically of what the atoms look like. And that's just not a priority when the people who are working on this are entirely concerned with mathematics, because they can make predictive statements about things without having to face down what the actual physical landscape looks like. I think that's just a bit unfortunate. So, you know, spin is another really interesting thing. Charge is another really interesting thing. These concepts that are just parameterized but not actually given physical representation. And we talked about that a fair bit last time. So I made the case to you that when you have a wire, it actually, all of this motion that we call charge that the surface of the atom is doing results in some equatorial motion. By the way, I was reading a bit more, working on a book with my wife about this right now, just this physical visualization of the atom and magnetism and light and gravity, electricity. And it's interesting because a lot of the super bosses of the science world worked on a very similar project in the 1800s. So Lord Kelvin, Maxwell had a very similar idea. They actually called it a vortex system. They were still thinking about this ether stuff, this fluid that must be everywhere. And they were locked into this thought that the atoms were bathed in this fluid, and so they were desperate to detect the fluid that they thought was separate from the atoms. And it's really sad because their ideas were really, really close to what I'm trying to present to you guys here, in terms of the motions, in terms of magnetism being this equatorial motion of the atoms, and the electricity being the actual flow of the surface in a polar direction. But they were just locked into this idea that there was a separate magical kind of fluid called the ether outside of it that was responsible for transmitting all these forces. And so they abandoned it when they failed to detect it. It's really quite tragic, but makes for some incredible quotes, because these guys put all of this in their own words, so I don't have to. Or they put all this down in words, so I don't have to. So anyways, you can generate this magnetic effect. Presumably because all the atoms' surfaces equatorial are spinning like in a column. That's one way to think about it anyways. And they do have this extended structure which allows this force to be transmitted to a wire that's next to it. You have two of them going in the same direction. They tend to draw each other near because their motions are equivalent. If they're moving oppositely, so the current's flowing oppositely in the wires, they will push apart because they're sort of like batting against one another. And what happens is if you line all those equators up by making this little coil system, right, then you can synergize all that motion, right? They can all work together because all the equators of the atoms are all lined up in this case, at least the relevant surfaces of the atoms. So this is the basic electromagnet system, which I think is really the basis of all magnetism. Now, when it comes to something like the Earth or the sun, the theory is a little bit trickier, but the idea is essentially the same. The idea is that as the Earth is spinning with respect to all the fixed stars and everything else behind it, that this goop that's underneath is, in some sense, being swirled around in these nice little coils. And so the coils actually end up generating a field, which then synergizes, and you get a much bigger field effect as the result of it. So, it's a little bit tricky because what is a field? A field is really just a vectorized series of measurements or predicted measurements. It's like how much magnetic effect you're going to read at any given location, or that you think you will, which you do because those laws work out really, really well. But to say that the field itself is the actor is a bit crazy. That's like saying that the data was responsible for the effect. It doesn't really make sense. So the atoms are doing something. I try to give you guys a visual representation of what they might be doing. Does this make sense so far? Questions? Concerns? Yes.
Does this imply that like the inner core is not spinning as fast as the rest of the planet is?
That's a really good question. Can somebody Google that actually? Which one's going faster? I think that the idea is that these little eddies build up all around the core, and that they sort of work together to form this bigger field. The core ends up stabilizing it. But yeah, what's the rotation rate of the core versus the outer? Say the inner core versus the outer core. You could ask Google that maybe. Or Siri or whoever you're talking to. Slightly faster. Okay. Very interesting. So, a natural question, and this is presumed to be occurring inside of the sun as well. Now with the sun's a little bit weirder, and honestly, it's not really our topic here, but the sun is a much less stable system, right? It's flopping much more regularly. So the dynamics, well, we don't really have time to get into the core of the sun today, but there's very spooky, weird things about the core, and the predominant model is that all the fusion is happening in the core, and we will pick that apart next semester. Oh, all right, almost lost it. What did I want to say about that? Okay, so why does our magnetic field invert every 700,000 years or so? By the way, we're like overdue for it right now. And it does appear to be wandering from the North Pole quite dramatically in recent years. Yeah.
It's like, does it affect plate tectonics or anything? Like, what does it affect?
Yeah, nobody knows. There's always some catastrophists who think it's going to be the end of the world. Yes, and then yes, yeah. It might be a bad day. I don't know. I don't know how long it takes either. People aren't sure. Not that long, but less than a century. I don't think it's going to be the end of the world or anything. But yes,
How long does it take to like burn to flip?
it's very hard to tell, right? So the way that they look at something from 700,000 years ago, which is the last time this happened, is they see that there's actually basically iron that's in the crust, and you can see how the iron is magnetized. And you see that it's layers. This is quite interesting. So we talked about how the ocean's quite young, actually, only 200 million. The Atlantic floor, for instance, it's only 200 million years old. That gives you basically 200 of these cycles to look at. And what you can see is that as it's kind of spread out, that there's bands as it's spread quite regularly where the magnetic field is pointed one direction and it's imprinted by the magnetic field that's pointed the other direction. In terms of like narrowing that down to like a matter of days or months or years, I think that that's kind of like beyond the scope of what's possible. So it's anybody's guess. It's really, really weird. And it's cool that it's happening right now because we'll find out. But I don't think it's going to be a disaster. We don't really depend on the magnetic field for much other than keeping us alive in terms of not getting smashed by. I think the only real danger that I personally could conceive of, and this is like a black swan possibility, but every once in a while we get hit with a really big solar storm, right? A big chunk of the sun just pops off and crashes into us. Actually, it happens all the time. It just misses us usually. And there's a really cool, I totally recommend you guys check out the space weather daily reports from NASA. So you can see this beautiful reconstruction of a top-down view of the solar system. You can see the little plasma blobs flying off of it every day and where they're going and everything. So this happens a lot. It's kind of continually shooting off pieces of itself quite directionally, which is a whole other discussion we can have. When the magnetic field reverses, we will not have much of one for a few minutes at least, or for a few days, or for a century. I don't know. I don't think anybody knows how long it takes to actually go through the reversal process and restabilize. So what happens when the magnetic field in the sun breaks down is that it gets really chaotic before it becomes repolarized in one direction. So if it took 100 years and we didn't have much of a magnetic field for 100 years, that would be a rough century. Primarily because the sunlight essentially and going outside would be a little bit on the dangerous side, I would imagine. And then on top of that, if we got hit by a really nasty solar storm, that could be problematic. Yeah. Yeah, it definitely has. It's drifted this is something we could pull up too, but it's moved something crazy, like hundreds of miles in the last century from the North Pole, right? It's normally centered on the pole, and it's been drifting down. So that's the only evidence. And I guess the fact that it happens quite regularly at these 700,000 year intervals, and that 700,000 years is up since the last one.
Sorry, this isn't even a silly question, but how do we know that it was 700, whatever the number you said? How do we know that?
So they look at they look at the age of essentially these beds on the ocean floor. So they look at the age of the beds based on regular radiometric dating that we've talked about. And then they look at how many there have been since the age, and they're at regular intervals. So they think that as either the seafloor is expanding, that's one way of looking at it, or as the goop is coming out of the center of the ocean and filling it out, in either case, there's still a clock available to you there. So you can say, well, there's been 200 of these bands in the last 200 million years, so it happens about every million years, something like that.
I looked it up. It has moved. Magnetic north has moved 600 miles since it was discovered. Her first precise location was measured.
Okay.
It says the rate of change.
It's speeding up, yeah. 600 miles, that's not crazy. It's moving south, right? From what I understand, kind of like down towards Greenland, which is quite interesting. Yeah, pretty weird. Should be cool. I don't know. We'll see. Yes.
So if it flips and there's a big solar storm and like it hasn't restabilized, like we would just get hit with like a lot of radiation.
Yeah. Yeah, essentially. You know, we do get hit by really nasty solar storms quite regularly. Well, every, century or two. The last one, of course, was at the birth of telecommunications. So there was only telegrams at the time. It's called the Carrington event. It was bad news even for the telegraph system. So it fried a bunch of different communication ports and stuff. This by itself, even with that was with a strong magnetic field protecting us. That's still a serious concern for our communications infrastructure. And the last time I talked to somebody at NASA about this, they were trying to come up with contingency plans for how to power down parts of the grid as they were being exposed to this so that they wouldn't jeopardize the whole thing. Because the way it's set up right now is, all our power systems are connected. So we're connected to California, connected to Nevada, blah, blah, blah. And so you would want to make sure to isolate the systems that we're going to be taking the brunt of it. And that's kind of the best plan they can come up with, but it's going to be bad. It's going to happen. That's going to happen at some points. The question is, are we going to be prepared to deal with it or not? And I do see people thinking about it more now than ever before. Yeah. Mhm. So the difference about the moon is that it doesn't appear to have any of that liquid stuff to do the actual magnetism in the first place. So if it had a magnetized core, it's long since dissipated. So permanent magnets aren't permanent forever. They will maintain that magnetic character that you imprint on them, but only for a certain amount of time. The atoms in there are going to eventually, just from thermal motion and so forth, they will get rid of all of that nice alignment that they had. Because really what you're doing, especially in permanent magnets, you're really just aligning all of those atoms to one another in such a way that they can have that cohesive motion of their surfaces and actually produce this magnetic effect. So they're all going to kind of relax and go back to the way that, some sort of chaotic configuration eventually. So yeah, who knows? I don't know. I don't know what people know about the moon's magnetic past. Like, I don't know if it's evident. I don't know if anybody's even really looking at that. It's obviously kind of hard to go there and get some rocks to look at. So, yeah. Any other thoughts on that? All right. So that's our magnetic situation. That's magnets. To the best of my ability right now. Oh, this is actually one thing worth considering. So, why would it invert? We didn't finish that question. Any ideas? Like, why does it periodically just turn upside down? It's pretty weird. So nobody knows, but I think that there's some insight in this experiment. You guys seen this from the space station? So this is called the tennis racket effect. It's a brutal mathematical problem, but the interesting story behind this, which I'm going to have to tell this story again next semester when we talk about atomic spin a bit more, because I think something like this actually happens with atoms as well. If a body is not perfectly spherical when it's spinning, if just a little bit more stuff is on one side versus the other, which is almost inevitable because nothing's perfect. What happens is that eventually you develop a little bit of an instability in the rotation. It's going to just start spinning slightly off axis. And what happens is that those start to feed back and get more intense. And at some point, it essentially gets so wobbly that it flips over and it'll restabilize in the other direction. And so what's kind of funny about this effect is that actually the Russians discovered this first in their space station, or one of their spacecraft, back during the Cold War years. I think this was back in the 60s or 70s. Must have been the 70s. And when the Russians discovered this, they kept it secret for 10 years. Anybody know why? They were really afraid that the same thing was actually going to happen to the whole Earth itself. So they were like, wow, if this is an effect that happens, it's very possible that the entire Earth will just flip over every once in a while. And so their scientists were completely convinced that this was at least a logical inevitability, and that if they told people about it, people would freak out, essentially. The American scientists came along, people talked about this later. They do not think that it will happen with the entire Earth. However, it does seem to be a situation that is plausible, at least with the core itself. Now, if the core being this nice stabilized magnet, right? The core being an iron core, if the core itself actually were to invert, it might just have enough momentum in it that it could get the goop kind of polarized in the opposite direction. And so you might have an inversion as a result. There could be something similar happening in the sun too. And there's more to say about that next semester, especially when it comes to making sense of Mercury's really weird precession. But I'll save that for next semester. What do you think? Maybe. It's a cool experiment anyways. So yeah, that's called the intermediate axis theorem. If you want to beat yourself up with some math, check it out. I think there's a really good Veritasium video on that one. All right. So the other thing that I want to talk about today is how all of this transmits down, how all of this magnetism plays out on Earth, how the electrical circuit of the sun plays out. I want to finish up talking about the atmosphere because on Thursday, we're going to talk about the origins of life on Earth, and then we're going to move into the other planets. So this is kind of our last push with our own planets. And I've spent kind of an inordinate amount of time on our own planet because I think it's the one we have most data for, let's put it that way. And it seems to be, in some ways, characteristic of a lot of things we see out in the universe and in our solar system, including these magnetic field effects and process dynamics and all that stuff. So if we understand it on Earth, everything else that we're going to talk about in the solar system make a lot more sense, or at least understand the possible explanations for these things. So there's this really, the source of a lot of our concern with respect to this magnetic field is this stuff called the solar wind, right? The solar wind is really poorly understood. In fact, I don't think that it was even much discussed as a phenomenon until the 70s or so. Actually, this guy, James Webb, who the big space telescope is named after, did a lot of the pioneering theory. That's why they named the telescope after him. But he really worked a lot on this on this solar wind stuff. But essentially, the sun, like a fire hose, is just spraying off all sorts of charged material, right? Really, really charged and fast-moving stuff. And it's really weird because the solar wind actually gets faster as it moves away from the sun, which is quite mind-bending if you think about it. But on the other hand, we can make sense of that because the gravity is also falling off as it moves away from the sun. So it has a lot of momentum, but the gravity is dissipating. It's sort of like falling upwards or something, if you can imagine that, or being shot upwards as a rocket or something like that. but it's still quite bizarre. And there seems to be a really serious system that's created as a result of this. A lot of it is flying out equatorially. A lot of it is making its way out to the edge of the solar system and then coming back around again and making a closed loop, which we call the heliosheath. There's an entire structure to this business, and it's all very poorly understood at this point. But the Earth is just sitting in the middle of this stream. And so the nice thing about this whole discussion with magnets is that the magnets, because of that magnetic action, when you have a bunch of atoms like the ones under our feet, all kind of synced up and aligned in some nice way, they're able to deflect all of those incoming charged particles really easily. And that's why we love the magnetic field so much. So, you know, the reason that a lot of that gets confusing is because, so what a lot of times you'll hear that the solar wind is composed of plasma. So what the heck is that, right? So anybody, chemistry people?
I mean, it's like a different phase of matter. It's like weird. It's like a very hot, liquid-ish thing.
Yeah, it is a weird, different sort of thing. Most people try to not really define it too much, other than saying that you have a separation of charge in some sense, right? So you'll often see it modeled as like a bunch of protons, right, nuclei, and a bunch of electrons, and they're all just a C together, right? Technically, a metal is the same thing, by the way. You can actually define a metal. This is pretty hilarious, but you can call it a degenerate electron gas, which is very similar. Which really just means the electrons, like it's hard to say where the surface of one atom stops and then the next one begins, I think is a more rational way of looking at it. The same thing seems to be the case with depressurized gases. So gases that are in outer space are very different than gases that are here on Earth, because remember, guys, we're under tons of pressure right now. You can't feel it because it's equalized with your internal body, but none of that pressure exists in the vacuum of space. And so what happens is those atoms have this unique ability, when they're not being crushed against one another, to be essentially electrically in contact with one another, which is quite interesting. So, one way to think about that might be that the actual shells of the atoms are much larger in space. Certainly, they're able to conduct with as little as, I think it's like an atom per every cubic centimeter or something, right? So the atoms are essentially really, really distributed throughout space in a different way. So I think that's the best way to think about plasma, is as depressurized atoms. Now, you can see this actually whenever we look at these like lamps, right, that have plasmas in them. Those lamps are under vacuum, right? So you can't actually put current through a gas unless you pump it down so that it has very few atoms in it. And nobody's really done a great job explaining why that is. But I think that if you really start to think about the atoms as physical objects, that when they're under a lot of pressure, like on Earth, that they're squished down a lot tighter, right? And so there's a lot of actual space in between the shells of the atoms in this room compared to the ones that are out in outer space. They're a bit more out, right? So they're able to conduct electricity a lot better. And the same with the ones in the tubes or whatever the heck we have going on above us right now. These are a bit more complicated because there is a plasmatic gas, but it's also illuminating the surface, which is fluorescent. So that's how we get the actual light. The light that's being generated by the plasma in these tubes above us is actually not visible to the eyes. It has to go bounce off of the fluorescent lining for us to see it. That's neither here nor there. Okay, does that make any sense at all? All right, think about it, chew it over. Okay, questions? Guys, yes.
Plasma, like what's inside of a lava lamp.
A goop of some sort. Yeah, it has that kind of like, it has that sort of vibe to it. I mean, the fact of the matter is that it is a really poorly defined substance from a physics standpoint. From a accounting standpoint, it basically just means that the gas has the ability to become charged all of a sudden. And that's really weird because gases often aren't electrically conductive. But once they're depressurized, then they are. We call them plasmas all of a sudden. And so like the textbook definition is just that, the electrons have left the atoms, they're flying around. It doesn't really make any sense, but it works from an accounting standpoint. Nobody actually thinks of an atom as having this like cluster of protons and neutrons in the center and little bowling balls of atoms flying around the outside. That idea it was never really taken seriously. It's just a really nice, easy accounting way of making sense of this action that we call the electron. What the heck is it? And so, yeah, I just, I'm interested very much in what the atoms are actually doing to account for these behaviors. Yeah.
Got the difference between plasma and supercritical fluid.
Oh God, supercritical fluid. Supercritical fluid. This is like gets into phase states, which we should talk about eventually because we have a lot of weird fluids inside of fluid-like things inside of some of the outer planets. I believe supercritical just means that it has the ability to act as a solid, liquid, or gas at any given point. Plasma, and that's under usually a tremendous amount of pressure or heat or something like that. But and of course the electrical properties do change at that point. But plasma, we can really just think about one atom, whereas phase changes, we have to think about groups of atoms together. Yeah.
It's a good example of a super.
You can have supercritical water, which is quite interesting. You can check out these YouTube videos where people will get water to like a supercritical phase where it's liquid, but it's very, very cold. It's below zero actually. And then what happens is if you like tap the glass, it'll just freeze really fast. So if you disturb it somehow, it'll snap into the solid phase. So if you cool it properly, you can get it actually. I'm not sure how they do it. Yes.
My fridge does that, my water bottle. I'll pull my water bottle out and it won't be frozen, and then I'll start drinking it and it'll just freeze as I.
Wow, that's cool. That's cool. Yeah.
My like favorite thing ever is I used to remember how long it was, but I can't remember anymore. But you would put a water bottle in a freezer for a certain amount of time, and then as you pour it out, it will start hardening and it'll turn into slushy as you're.
What the heck? I gotta try. You guys,
you can like hit the bottom of your water bottle and it'll freeze right in front of your eyes.
you guys know more about this than me. That's crazy. That sounds awesome. I need to play more with my freezer, I guess. Yeah, but there's weird. So the phase diagrams are really poorly understood. It's very bizarre. You inherit this story that you put a liquid under certain pressures, temperatures, you're going to get a certain phase. It seems to be a little more complicated than that, unfortunately. Yeah. GAC? This like yeah. Yeah. Well, water is solid if you hit it too. That's why people are jumping off the Golden Gate Bridge all the time too. Just to take the conversation down a notch. Yeah, you hit a body of water going 75 miles an hour, there's not much left of you. So it's like it has a really solid character too. What's up? Okay. Don't do it. Don't try this at home. That's not a good way to go. I heard a really interesting study recently. There's people are always jumping off the Golden Gate Bridge. Anybody ever lived in San Francisco? No, I used to live there for many years. People are always jumping off the Golden Gate Bridge, but not everybody dies like miraculously. Some people hit the water just right, they hurt themselves, but they don't end up dying. And 100% of people who jumped off the Golden Gate Bridge that survived said that the minute that they left the rails, they were like, "Oh no. I thought that was really profound. I think that it's really interesting that 100% of people who survived, and I think it's not terrible. It's like 10% or 20% of people survived who jumped off of it, and every single one of them regretted it the instant they let go of the rail. So that's something to consider. All right, what else do I want to say about this? Okay, so this is all quite interesting. This pressure discussion actually flows kind of nicely into the atmosphere. So like I keep saying, is that you depressurize gases and they take on this plasmatic state, right? They become very conductive for whatever reason. And the interesting thing about our atmosphere, obviously, is that it's most pressurized down here on the ground. So this is actually pressure on the left side versus says altitude, right? So you see that it's actually becoming more and more pressurized the closer you get to the ground. The result of that means that the higher you get up, the more conductive the atmosphere becomes, right? Because it's becoming depressurized, it's becoming plasmatic in that sense, right? It's becoming, another way of putting it is it's becoming ionized up there, right? Now, this turns out to be pretty important, particularly if you want to make sense of weather here on Earth, right? So most of the time, we think about weather as being the results of temperature and pressure, right? So the hot air expands, you get these pressure fronts, it leads to the condensation of water and so forth. As you get hot and cold cells meeting each other, and you get precipitation and storms and all of this. But there's an electrical quality to it too. I don't know if you guys ever noticed, we don't get a lot of obvious lightning storms out here. I grew up in Ohio, and let me tell you what, we got insane lightning storms every summer in Ohio. It was absolutely gripping sometimes. So what's up with that? Anybody understand how lightning works? Yes. Yeah, it definitely is. So essentially what's going on here is that you have that all of that ionized air up at the top of the atmosphere, right? It's very conductive. It builds up a charge as a result of that stream of solar wind, right? Kind of like if you rub a balloon, right? With a piece of wool or something, right? You can build up static charge on it. Very similar kind of thing, actually. The result of it is that down on the Earth, and by the way, a lot of that solar wind is still streaming in through the poles, right? There's a little hole. Let's not say a hole, but there's a gap, a weaker part of that magnetic field up towards the poles where a lot of this can stream in. The result is that you build up a differential in the charge between the ground and the upper atmosphere, right? So in a sense, the sky and the Earth form a kind of capacitor, like a battery, very similar, where you have a differential of charge. And if you put something across it, a wire of some sort, you can relieve that tension between those atoms on the floor and up in the sky. So what happens with lightning is that the air is actually a really good insulator. It does not like I told you, it's under pressure, it's bouncing around. It's very hard to align those atoms to one another in order to conduct electricity. But if there's enough charge difference, if there's enough tension between those atoms at the top and those atoms at the bottom, they will start to align themselves along the way. And the result of that is that you actually have a breakdown of those. You really have a breakdown of that atmosphere, and you form this little tiny wire from the top to the bottom, usually from the clouds down, but they can go amongst the clouds. You basically could get this really big charge differentials that play out by essentially ionizing the air and ripping those molecules apart so that they form individual atoms which are capable of doing the dance that we talked about with electricity last time. Pretty crazy. Make sense though? All right. What I want to say about that. Oh, there's something we should touch on. We mentioned that the Earth is in some sense transparent to ultraviolet radiation. Obviously, ultraviolet radiation is kind of rough on DNA too, for whatever reason. Has the ability to shake DNA apart. So we don't want too much ultraviolet radiation down here. We have, fortunately, a molecule in the atmosphere called ozone that is capable of resonating with that frequency really, really nicely. And the result is that it screens out a lot of the ultraviolet radiation. Now, there's this story, I think this was in your textbook. Textbook's always updating. I'm not sure if they're still telling this story. But they like to tell this story about the ozone. This was a huge news story when I was a kid. It was like the triumph of science. People noticed that there was actually a hole forming in the ozone back in the 80s. And they actually did something really cool, which is they realized that a very common refrigerant was leading to the breakdown of ozone in the atmosphere. And they actually got together and made a worldwide ban on this substance. And everything got better, but did it. So it was often like heralded. This is a picture all the way up to 2016. Now the problem is that the ozone hole appears to be coming back, and nobody really knows why because we've gotten rid of those particularly pesky chemicals. And so, could it be something of a natural cycle, some feedback loop? I don't know. It's quite interesting, but yeah, it did shrink momentarily there back in the late 80s for a minute, and then it came back. So I don't know. It's very, very bizarre. I don't think that, unfortunately, the triumphant story of us healing the ozone layer doesn't seem to be uh, quite as simple because we're still dealing with it again today. Now, I did want to mention, I know we talked about this a little bit last time. Our atmosphere is almost entirely nitrogen. We're going to see a lot of nitrogen as we creep through the solar system soon. We have a good amount of oxygen. It doesn't appear to have always been in the atmosphere, which is quite interesting, and we'll talk about that with the origins of life. And then we got a bunch of these like trace gases too. So, you can see the layers of these. Neon, carbon dioxide, krypton, helium, xenon, a bunch of just insignificant amounts of stuff. Maybe it's significant and we don't realize it, but certainly the carbon dioxide has gotten a lot of attention lately. But yeah, it's a mostly nitrogen atmosphere. So that's kind of cool if you didn't realize it. All right. So where did the atmosphere come from? Is a natural question too. And I think we've kind of played with this idea a little bit already. Well, could have formed exactly as it did with the rest of the Earth, accumulated from debris left over from the formation of the sun. This is probably the one that's in your textbook. Another interesting idea is it could have come from the interior being released through volcanic activity. So I don't know if you guys realize it, but when volcanoes explode, what's the main thing that comes out of volcanoes? Nope. Anybody? Yep. What kind of guess? Some, yeah. It's mostly water, actually. It's a lot of water vapor that comes out. Water, of course, has a big oxygen sitting right there in it. And it can be naturally broken down through lots of chemical processes, but particularly through electrolysis. So being electrically stimulated, you can actually break water apart. So there's a lot of geochemical processes that could have generated the oxygen in our atmosphere. Another textbook explanation, the atmosphere could have come from impacts by comets and asteroids. I guess so. Like I said, the standard explanation for where the water came from on Earth was, I don't know if they're still doing this in the textbook, but comets, I guess, was what they were saying, at least when I was in college. That seems less and less tenable as we go on. I think that yeah.
The one that I learned is the volcanic one.
Okay, cool.
Didn't the water come from, I guess, after the atmosphere was created from all the eruptions, then it like just rain.
That's certainly one story. There's a really interesting Nature paper. I wish I pulled it up. Maybe one of you guys want to do this for your final project. There's a lot to be said about this. Where did the atmosphere come from? There's a Nature paper, I think 2 years ago, that showed a model for how the Earth could have at some point had a really enormous hydrogen rich atmosphere, and that the hydrogen reacting with the silicon dioxide, the sand. Remember, our Earth is largely made out of silicon dioxide, so that's a lot of oxygen lying around. In addition to the iron and nickel and all this other stuff under our feet, there's a lot of just rock, silicon dioxide in particular. Scientists now think there's something like 7 times the amount of water in the oceans under our feet, just in the form of rock, like hydrated rocks, right? So silicon dioxide, rocks, and there's been proposals that, as far as I can tell, are quite reasonable for how a very primitive, very different looking Earth could have evolved chemically into having an atmosphere and oceans, as far as we can tell, because water is a natural byproduct of lots of different chemical reactions, including cooling reactions for the most part. You get condensation of water and so forth. So there's a lot of possibilities there. That's a really interesting one if anybody wants to do it. I can point you towards some more papers too if you're interested. Thoughts? Questions? And you guys are so depressed today. This is rough. Yeah.
Studied the, right, let's just go down right now. The, like, level, or like the amount. Sorry, the ratio of water that we are, has that increased?
Us human beings? Jeez. Yeah, I don't know about that. I mean, even the most standard textbook models are gonna peg the early Earth as having lots of water, from what I can tell.
Okay.
Yeah. And life appeared, not that long afterwards, but a little while. And so the idea is that life kind of makes sense to be underwater first, particularly because the early life forms didn't seem to have the ability to process sunlight directly, right? So they were living off of some sort of stuff in the water, some sort of chemicals. There's really primitive bacteria that can metabolize rocks, which is really crazy. So maybe there was some of that going on. Those are really the mystery of the origin of life is one of the coolest stories, and that's what we'll do on Thursday. Any other thoughts? My poor depressed students. Yes.
So just last week, we had an article or whatnot, video something like that. I don't know. It was article I read was talking about how Mars appears to have like a large amount of water that's all around. This is like a recent
In the ice caps, yeah.
from not the ice caps.
Hmm.
It's actually from their in the name. It was not one of their rovers. It was like a land just landed and they got like seismic activity. From that, they're able to.
Interesting. I saw this stuff about the ice, like below the ice caps, but like subsurface, like hydrated minerals or subsurface lakes or what?
But they were saying like hydrated like minerals most likely.
Yeah, I think that's the most common one.
Like this be like 11 to 20 kilometers beneath the surface.
Yeah.
I'm just talking about there being water here on Earth beneath the surface.
I mean, I just think it's really fascinating. Like the hydrated minerals below the earth, like if it was only a little bit and it was kind of rare, I think it would be less interesting. But the fact that there's so much of it, I think really puts to bed these ideas that water had to come on comets or something crazy like that. It's like there's plenty of water in this planet from day one. Not to mention the abundant chemical reactions that you would expect if the Earth was in some sort of had some really primordial atmosphere that was hydrogen rich. I actually think that as we start looking at all these planets, I think you could make a very compelling case of how one planet evolves into the next. I'm not saying it's true, but it's very compelling because you have the chemical reactions available to turn something from a Jupiter into something, that's evolving something like methanes, that's then evolving into something that's a bit more, uh, oxygenated and so on and so forth. And you end up getting the possibility at least arriving that you have actual evolution of planets. So the Earth, the primordial Earth, we can take stabs at what it might have looked like, and I have my favorites, but it probably looked nothing like this. I don't think anybody thinks it did. It probably wasn't born with an ocean. And so how did that form? It must have been some sort of geochemical process. It must have been some sort of chemical reaction. And the details, if you guys have ever spent a day in a chemistry lab, you probably have because you all went to high school. Like almost every reaction gives you water as a byproduct. It's very, very common. So, yeah, there's not too much of a mystery there, at least in terms of where the oceans came from and stuff like that. It doesn't seem to be that difficult to make an ocean if you have a lot of chemical reactions going on for a long time. All right. All right, we talked about this a bit. Talked about that a bit. Oh, I wanted to show you guys one resource. This is really cool. Have you guys ever been to null school before? So it's quite interesting if you're actually wanted to open this up so we can play with it. I think see if I can. It's so hard to keep track of the mouse up here. There it is. Is it? No. All right, I'll just have to open it. All right, it's pretty cool. All right, so you guys can check this out. It's called earth.nullschool.net. This is one of the coolest ways, I think, to get a grip on the way that weather patterns work on the Earth, and they're all pressure dependent. So what's really interesting is, anybody fly planes? Any pilots? Yeah, a little bit. Yeah. So planes and pilots, they actually measure their altitude by pressure, right? So the way that this works, this is going to be not easy for me to pull off without being able to see. There it is down in the bottom corner. Come on. Okay. What we can do is actually zoom into different altitudes based on the pressure. So this little dial over here, it says HPA. So this is units of pressure. So if we go to the lowest pressure, we're going to go highest up in the atmosphere. And what's really interesting is you see this really banded structure, right, where the atmosphere is essentially moving in a couple of different bands in different directions and so forth. But as you go down in pressure and start to move your way down towards the surface of the Earth, you get very different pressure systems starting to appear, to the point that you actually end up with the weather patterns that we're all familiar with. Let me see if I can find us over here, make sense of this dreary weather that we're having. Yeah. So what happens is you actually have layers, and the weather down at the high pressure regions is in many ways very much influenced by the currents in the ocean as well. The ocean actually has this ability to do kind of what the solid core does for the magnetic field of the Earth. It can stabilize it, right? It can actually keep heat present. It can circulate the heat, and it has this ability to, and of course you have evaporation at the interface. So the weather down on the surface is very much influenced by the oceans themselves, which cover a pretty appreciable piece of the Earth itself. But as you go up into the ionosphere, you get something that's quite laminar and very consistent. And what's interesting is, when we go and look at some of these gas giants and so forth, you will actually see that, where's my mouse at? There you are. You'll actually see that Jupiter and some of the other guys have atmospheres that look a lot more like this on the outside, right? They're a lot less churned up and so forth, because they don't have that surface interaction that we have going on here on Earth. And it's really cool because you actually start to see that as the planets evolve, or if you step down towards something that looks more like a planet versus something that looks more like a star, you actually see you can almost see, you can clock it, right? So brown dwarfs and so forth will have a much more laminar surface like this, very unidirectional, compared to like a Jupiter, which is a little bit more chopped up, and you actually start to get little storms forming and stuff like that. Presumably because there's just less stuff and you have more of a pressure differential on them. Then you get down to something that looks kind of more like Earth, or a sub-Neptune or something. It's going to be a bit more diverse of an atmosphere that has different layers, and it's quite complex. Thoughts? All right. Poor people. All right, guys. Next time I'm going to bring my wife in. She's going to talk to you guys about origins of life on Thursday. So please come, and that will be fun. What else do I want to say? Next thing we're going to do is start looking at the other planets. So we're going to go to Mercury, Venus, Mars, make our way through the solar system. I think that we have covered everything I want to say about Earth. And you guys don't have any more questions? Any questions? All right. Well, try to cheer yourselves up. Get out there and vote. And I'll let you guys out early today. And I'll see you on Thursday. We'll do the origins of us. All right. Good luck, guys.